The process of cell division is dependent on the cell cycle, which contains 4 phases for regulating cell growth: growth phase 1, synthesis phase, growth phase 2, and mitosis. The key cellular components for regulating progression through each phase of the cell cycle include Cyclin D CDK4/6, Cyclin E CDK2, Cyclin A CDK2, Cyclin A CDK1, and Cyclin B CDK1. The ultimate checkpoint for cell division in the cycle is within G1 and is known as the restriction point. This is the point where if the cell can coordinate the presence of necessary molecules, cell division is almost guaranteed to follow. However, if these molecules cannot be coordinated, then the cell will enter what is known as G0, where the cell cycle progression is postponed or abandoned and the cell goes into a resting state. Cyclin D levels are increased following the activity of external growth factors, leading to Cyclin D CDK4/6 complexes, in essence beginning the first phase of the cell cycle. The effect of Cyclin D CDK4/6 lies in its interaction with retinoblastoma, which begins the cell cycle bound to E2F. Cyclin D CDK4/6 complexes act by phosphorylating retinoblastoma E2F, changing the conformation of retinoblastoma, resulting in the release of E2F, which is now free to upregulate transcriptional expression of Cyclin E. As Cyclin E is translated into protein, it binds to CDK2, forming Cyclin E CDK2 complexes, which further phosphorylate retinoblastoma, releasing even more E2F in a positive feedback cycle, which is important in surpassing the R point. Inhibition of Cyclin E CDK2 activity is carried out by a molecule known as P21, which is from the CYP-KIP family of inhibitors. P21 also binds to Cyclin D CDK4/6 complexes, with a higher affinity than for Cyclin E CDK2. However, in this instance, it increases its activity. Free P21 is also degraded by Cyclin E CDK2 activity, which along with the sequestering of P21 by Cyclin D CDK4/6, ultimately leads to increased Cyclin E CDK2 activity and cell cycle progression. When a cell experiences DNA damage, hypoxic environments, or any other cellular abnormalities, it must have a way to avoid progressing through the metabolically costly process of cell division, and to give it an opportunity to either repair itself or undergo apoptosis. The regulatory molecule responsible for carrying this out is P53, which acts by increasing the amount of P21, leading to the binding of both Cyclin D CDK4/6 and Cyclin E CDK2, ultimately resulting in prevention of the cell cycle and entry into G0. An example of an abnormality in one of these processes leading to uncontrolled cell proliferation or cancer can be seen in breast cells, where normal breast cells undergo cell proliferation through the binding of estrogen to specific receptors known as HER2 receptors in the cell membrane. This leads through intracellular signaling to increased expression of Cyclin D. In some cases of breast cancer, breast tissue cells express an abnormally large amount of HER2 receptors, resulting in more intracellular signals, upregulating transcription of Cyclin D. This increased amount of Cyclin D leads to an increased amount of Cyclin D CDK4/6 complexes, leading to uncontrollable cell proliferation. When these regulatory processes are uncontrolled, such as overexpression of cell cycle activators including Cyclin D CDK4/6, Cyclin E CDK2, and E2F, or underexpression of the inhibitors, INK4, retinoblastoma, P21, or P53, abnormal cell proliferation can occur.